Good morning, everyone. So, today's topic is we got a steel beam, and apparently this steel beam came to one of the guys that I know, and evidently they put it in the ground, and the pattern that they put it in the ground at was like this. They're building a building. They got 3 of them on the long edge, 2 of them on the short. This one was okay, this one was okay, and this one was okay. But this one, and this one were about 2.5 inches too long. He spoke to many of his other logistics personnel, like who supplied the beam, who cut it, the engineer that decided on what length it should be, and it's due to thermal expansion, apparently. I find that to be kind of a little weird considering it's only 4.5 or 40 feet long. That doesn't really make a whole lot of sense to me. So what he asked me to do was to actually do the math and figure out if it's true. Is that something that can really actually happen that much on a normal day out in regular sunlight? I think last week it was like 60, 70 degrees. Hell, it could be 100. It doesn't really matter in this case. But he went out there, and that's what they told him, thermal expansion. They're not going to take it back. They don't want the money back. Nothing like that. They don't want to deal with it. So what we're going to do is we're going to do a little bit of simple math and decide on whether or not that's even possible. So you got delta L, which is change in length. And you got alpha. That's the coefficient of expansion for steel, mild steel. This isn't like austenitic, stainless, or anything like that. Another thing you got is L subscript 0, which is your starting length, which we're just going to call that pretty much what they ordered it as. He ordered it for 40 foot. But what we're going to do is we're going to do everything in inches because that's the result of the problem. 40 foot times 12 is 480 inches. And then delta T is change in temp. Now mind you, this has to be in Celsius for this to work with that coefficient, because that coefficient is length per degree Celsius. What we're going to do is we're going to use inches. It doesn't have to be standard units, it doesn't have to be meters, it doesn't have to be kilometers, but what it does have to be is these two right here need to be the same measurement. These two coexist with the same numerator denominator for canceling out to result in the final, because change in temp in this case will be inches per degree Celsius. The original length will be Celsius, and we're trying to figure out what this is in inches. Well, these two cancel out and you're left with inches. So you can make this anything you want as long as these two match. If you're doing this equation in inches, this is going to result in inches. Otherwise you got to do a conversion, and it's kind of a big pain in the ass. Normal steel usually runs 11 to 12.5 is what you typically run for the coefficient. We're going to use 12. It's 12 times 10 to the negative 6. So we're just going to put the zeros in there just so it looks nice and pretty. So that's your coefficient. Then you got the original length. We're going to do it in inches. And the change in temp. See, the way change in temp works is you got temp final minus temp initial. We're not going to fill in final. We want to solve for final. So we're just going to put in the original temp. We're going to say 68 degrees, which comes out to 20 C. You know, the standard. Hopefully you can see all this. But now we have two variables. So how do we know which one's which? Well, it's easy. The change in length is 2.5 inches claimed. So now we have our inches, they match, and this is inch per degree Celsius. We have Celsius, so now what we gotta do is we gotta solve for the final temperature to get 2.5 inches. We're looking for what temperature it would have to be outside for this to be 2.5 inches longer. So what we do is we first take our coefficient times our inches, and that gives us 0.00576, and then we distribute that, this times this, so we get T final minus this number times this. That gives us negative 0.1152 equals 2.5. Why they make us do this, I don't know. But, alright, so we got this equation all set up. We're going to bring this over here, we're going to add it. That leaves us with 2.6152 inches equals 0.00576 final temp. Alright, so final temp is pretty much going to equal 2.6152 divided by our number on the right, 0.00576. The final temperature, if it expanded 2.5 degrees, God, you can't see anything on here. If, big if, the material temperature would have to be 454 degrees and 3/10 just to reach 2.5 inch of change. 450 degrees Celsius just to get it to expand 2.5 inches. This is not thermal expansion. Now that we've busted that, talk a little bit why they do that. One, apparently the engineer is like 23 years old. Two, once it's cut, let's say they're cutting it out of 50-foot beams. The problem is they sit there and chop this out to make a 40-foot. The issue comes along that now they got 10 foot of scrap. They cut it out of another one, so they got a 10 foot of scrap. You just gave them a 40 foot of scrap, plus they got to cut another one, which gives them another 10 foot of scrap. The cost in scrap alone costs more than the beam is actually being sold for at this point because logistics cost so much. So, of course he's going to lie about it. He's going to sit there and say, yeah, we gave you the right length, or you did something wrong. So I thought about it. There's three things that could have happened here. Thermal expansion, we ruled it out. The other thing I thought of was maybe when they put it in the ground, this is the ground, there's your beam. "40-foot fall beam." Maybe the other ones were put in wrong. See the difference there? It's that gap. Maybe they put them in the wrong depth. The other thing that could have happened is the thing that everybody's trying to avoid, a bad cut. chances of a back cut is probably pretty high. If they were doing this, say, against a saw stop or something like that, or a fence stop, maybe they bumped it one time. Maybe the guy got tired, when he went to set it up on the table, bang, slammed into it, moved the stop over. It's possible. A beam that big can move a stop 2.5 inches and somebody probably wouldn't notice, and then next thing you know, you got consistently wrong cuts. So what they are is they are all precise, because they all repeat themselves 2.5 all the way across 3 of them, but they're not accurate because they're not on target. The difference I'm talking about here is if you got a target and you're going like this, it's not accurate and it's not precise. If you go like this and hit a target over here, this is precision, but it's not accurate. To hit all in the middle is both precise and accurate. Accuracy is the ability to hit the target. Precision is the ability to repeat accurate shots. And the problem is when they got in there, they got a precision cut with an inaccurate result. Because once they bump the fence over, of course all the pieces are getting cut the same, but they're not the length asked for. This is just a short video. This is Rob with Sine Wave. Keep in mind, I'm just in school, but in my theory, let's look at a cross sectional of this beam. Okay, so we got a 40-foot beam. We only talked about thermal expansion this way, right? That's not the case here though, because in physics, you got 3 different directions. You got a width expansion, a height expansion, and you got a length expansion. So unless we're getting expansion like this, it's not actually a true number that I just gave you. 454 may not expand fully this way because the atoms would move around, or molecules would move around to expand every direction. If this only expanded this way, that is because something else is equally pushing a net force on everything else. So there's no expansion here, here, or here. It's just this way. So, if you got anything else on it, or you can think of why somebody did it to your job site, by all means, put comments down there. It's wide open. Yep, that's Rob with Sine Wave, and thanks for watching, guys. Alright, ladies, gentlemen, guys on the work site, something else I want to bring up. I even forgot about completely. Alright, so you got this little building over here, right? You got these beams. One of them's longer than the other. Alright. Keep into consideration too. Alright, this is going for the guy that's out there. I want you to check on something here. You got this guy surveying. Make sure that when you're out there, this guy over here, can you even see that? Probably not. Where he's surveying, make sure the ground that he's on is level. Make sure the Trimble or the Bosch or whatever you're using to site survey this thing, where was the error found? Was it found here? Or was the error found from some guy over here with a measuring tape? Because if he is over here with a measuring tape, this is screwed up. If he found it over here, but the beams are the same length from the ground, you're on a slope. So, if you're on a slope, that's a problem. because you're going to take shots and they're going to run across. And what's going to happen is the angle from the first shot, the angle from the second shot, let's say it's 45 and 30. Over here, you're measuring the same beams on that slope as somebody didn't level out that system. And you could be looking at something like 27 and 39, which will make that system wrong. If this guy's wrong, but this thing's right, or this thing's wrong and this guy's right, you don't have a good you don't have your axis set up. You're not on level ground anymore. Make sure you check that system before you start calling people out. Measure both of them. This should give you the same reading this gives you, and this reading should be the same as this one. Otherwise, you're gonna look like the moron. Make sure you check that stuff. Surveying equipment is everything. Alright, this is Rob with Signway Specialties. If there's anything else you want me to investigate just for the fun of it, it's all anonymous anyway. Thanks for watching.